In this video, we're going to go over atomic structure practice questions. We're going to answer quite a lot of questions to find the wavelength, going to the photoelectric effect, and some many other things. So, the first question, what is the de Broglie wavelength of an helium atom of an atomic mass of 4.003 atomic mass units traveling at 1000 meters per second? Now, the de Broglie wavelength is given by Planck's constant over mass times velocity. Now we are talking of an helium atom. The mass which you've been given is in atomic mass units. So we need to convert these atomic mass units into kgs. Okay. So one atomic mass unit, 1 AMU, gives 1.6605 times 10 to the power negative 27 kgs. Now we want to find out 4.003 atomic mass units. How much is it going to give us? So we simply cross multiply there. That would be alright, 1.6605 times 10 to the power negative 27 multiplied by our 4.003. So that is giving us 6.647 kgs. Okay, 6.647 times 10 to the power negative 27 kg. So that is the value in kgs. So now we come here, the de Broglie wavelength is going to be Planck's constant, which is 6.626 times 10 to the power negative 34, divided by our mass, which we have found to be 6.647 times 10 to the power negative 27, multiplied by the velocity, which is 1000 meters per second. So that is going to give us, in the denominator, if you multiply 6.647 times 10 to the power negative 27 by 1000, should get 6.647 by 10 to the power negative 24. And then we get 6.626 times 10 to the power negative 34 divided by the answer that you have found. So the de Broglie wavelength we should be able to get is 9.97 times 10. Okay, now I think it would be important for us to consider what you've been given here. So in chemistry, this one has got 4 significant figures, that is 1, 2, 3, 4. Oh, this one has got 5 significant figures. And then this number which is here, 1, 2, 3, 4, has got 4 significant figures. So our answer should be to 4 significant figures. Therefore, the answer here is supposed to be 9.968 times 10 to the power negative 11 meters. So we can convert this one to a more convenient unit. Let's convert it to picometers. We can multiply. Okay. So we can just do the multiplication, converting it to picometers so that it looks much cleaner. So we will bring, because the meter is on top, they are going to bring the meter down. So in 1 meter, we've got 10 to the power 12 picometers. So this and that are going to cancel. So if you multiply by 10 to the power negative 10 to the power 12, should be able to get a wavelength that is 99.68. Alright. So our wavelength gives us 99.68 picometers. Alright, that will be our answer for the first question. So the second question we've been given, if an electron in the hydrogen atom makes a transition from an energy state of principal quantum number n to n is equal to 2. So if the photon emitted has a wavelength of 434 nanometers, what is the value of n? So we want to calculate the value of n after an electron transitions between energy levels. So I think just something that we need to be expecting is we have got something like that. So we know that an electron is going to transition, is going to go to the second energy level. Let's say if this is n is equal to 1, this is n is equal to 2, this is n is equal to 3. So an electron has found itself here. Now the question is, an electron in the hydrogen makes a transition from makes a transition from an energy state of principal quantum number n to n is equal to 2 if a photon emitted. So there is a release of energy. Okay, so a photon was emitted. Now I want to calculate where is it going to be found. Alright, so the first thing that we need to get to understand is when energy is emitted, that is, it is negative. So that is the first thing that is we need to understand. Alright, so the energy will be negative there. Okay, so we need first to find an equation where we are going to determine something before we can even go to finding out our answer that we want. So we know that energy is given by Planck's constant times the speed of light over wavelength. So we need first to find out the wavelength of this. Alright, we were already given the wavelength here. Okay, we need first to determine the energy of this electron, which was the photon which was emitted. After determining that energy, we can now use the relation of that energy we found in a Rydberg equation involving now energy levels. So in this one, we know that the energy, the Planck's constant, we know this is a constant value, that is 6.626 times 10 to the power negative 34 multiplied by the speed of light, which is 3 times 10 to the power 8, divided by the wavelength. Now the wavelength has been given in nanometers, that is 434 nanometers. So converting this number to meters, simply multiplying by 10 to the power 9. So the value now will be in meters. Therefore the energy that we are going to find here will be 4.58 times 10 to the power negative 19 joules. Alright, having found the energy, now we use the equation that we are that can be able to help us calculate the energy level where the electron transitioned from. So we know that energy is given by negative 2.178 times 10 to the power negative 18, and then 1 over n final squared minus 1 over n initial squared. Now because here the word is emitted, this word is telling us the energy was released. Now if the energy is released, we put a negative. So this energy that we have calculated was released, therefore it is negative 4.58 times 10 to the power negative 19. It should be equal to negative 2.178 times 10 to the power negative 18, open brackets, 1 over. Now the electron transition to the n is equal to 2 from n. So the final energy level is 2. Now we are squaring that. Minus 1 over the initial where it came from is the n which we want to calculate. Okay, like that. Now we want to make sure that this part remains alone. So the first thing, let's just try to divide. Let's divide both sides by negative 2.178 times 10 to the power negative 18, even this side. So what we are going to remain with is this, and this is going to cancel. So this part, so this, if we divide negative 4.58 times 10 to the power negative 18 by negative 2.178 by 10 to the power negative 18. Oh, sorry, this is negative 19. That was an error. So that is supposed to give us a value of 0.210284664, and then should be equal to this part. So that will remain 2 squared, which is a 4, then minus 1 over n squared. Alright, so that is what we are going to find. Now our aim is to find the value of n. We can take this part over the other side, and then we take this that side. So what we are going to remain with is 1 over n squared is equal to 1 over 4 minus 0.210284664. All right. So, and then we can do our subtraction. 1 minus that value which we have there should be able to get 1 over n squared being equal to 0.039715335. Okay, so this is 1 over n squared. So whenever we take the n on top, this is going to like come down. So n squared therefore is going to be 1 over 0.039715335. So the n squared is going to give us about 25.17919075. So from here we are going to take the square root on both sides. So therefore our n is going to give us positive or negative approximately 5, because energy levels can't have fractions. Now we don't take the negative sign of this one, because an energy level can never be negative. Therefore our n is going to be 5. So this came from the n is equal to 5 energy level. And this is true because when an electron which is in a higher energy level loses energy, it drops to a lower energy level. That is what happens. If you have got an electron there, if it loses energy, it's going to drop to a lower energy level. So very true. All right, let's go to question number 3. We want to calculate the wavelength of the p-fund line that is corresponding to n is equal to 6. So the wavelength of the p-fund line corresponding to n is equal to 6. How do we go about that? So the first thing that you just need to understand is, what do they mean by p-fund line? So that is the one we need to understand. If we understand what they're talking about by saying p-fund, then we are one man right to find the value to this question. Okay. So what we need to get to understand is, whenever an electron transitions to the first energy level, that is called the Lyman series. Okay. Let me just try to show the energy level so that we understand what we are saying. So in case you didn't watch the video, we have got a video on this one just talking about specifically what I'm talking about now. So whenever an electron transitions to the first energy level, regardless from where it is coming from, it can come from any other energy level. As long as it reaches the first energy level, that is called the Lyman series. So when it reaches to the second energy level, that is called the Balmer series. So when it reaches to the third energy level, regardless from where it is coming from, that is called the Paschen series. Now when it reaches to the fourth energy level, regardless from where it is coming from, that is called the bracket series. So when an electron transitions to the fifth energy level, regardless from where it is coming from, that would be called the p-fund. So this is where they have asked us to find. So that what we need to know is that the p-fund is a final state. It is coming from n is equal to 6. So these are written here are always the final states. Okay. The one where it is coming from will be given. In this case, just like it has been given. So our aim is to calculate the wavelength. Now we need to get to understand that wave number is given by the Rayleigh constant, that is RH, and then multiplied by 1 over n final squared minus 1 over n initial squared, like that. So the Rayleigh constant we use here is 1.097 times 10 to the power 7. It is in per meter. All right. And then 1 over the final energy state, because we're talking about the p-fund, that is 5. We square it minus the initial, it came from the 6th energy level, squared. So that should be able to give us 1.097 times 10 to the power 7 per meter multiplied by 11 over 900. So this should be able to give us about 13407.778 per meter, like that. Now we don't want the wave number. Our question asked us to calculate the wavelength. How do we find now the wavelength? Okay, so wavelength is simply the reciprocal of the wave number. So we have 1 over the wave number is 1340777.778. So this should be able to give us a wavelength of about 7.458 times 10 to the power negative 8 meters. So to convert it to a more convenient unit, let's multiply by, the answer is to the power negative 6 meters. So let's convert it to nanometers. So we know that in 1 meter we have got 10 to the power 9 nanometers. So therefore the answer that we are going to find here, okay, so the answer that we are going to find is 7.458 nanometers. So that will be our answer on this question. That will be the wavelength. All right. So the next question that we've been given, a certain electromagnetic wave has a wavelength of 625 nanometers. Now, what is the frequency of the wave? Now, we know that speed of light is given by wavelength times frequency. So I want to calculate the frequency. Therefore, the frequency will be the speed of light over wavelength. And we know the speed of light is 3.0 times 10 to the power 8 meters per second, divided by the wavelength, which is 625. Now it is in nanometers. To convert it to meters, we multiply by 10 to the power negative 3. I meant 10 to the power negative 9. It is now in meters. Okay, so what we see is this meter and that meter is going to cancel. What we are going to remain is per second, and per second is what we call as the hertz. So the answer we are finding is 0.633 per second. So we can also convert this value to a more convenient unit. Okay, that was 0.633. Let me just write that again. I've left something. So that is 0.633 times 10 to the power negative 6. Okay. So that should be our answer. Am I doing the right thing? All right, let me just replace on the calculator. Perhaps I might get a different one. So what we are saying is 3 divided by 625. That is giving us, so if we just divide these two here, the answer that I'm getting is 0.0048. Now multiply by, we have got 10 to the power 8 and 10 to the power negative 9. These are numbers of the same base dividing. So we simply subtract the power. So that will be 8 minus negative 9, which will simply be like that. So we are multiplying this number by 10 to the power, that should be power 17. So times 10 to the power 17. So the answer I'm finding is 4.8 times 10 to the power 14 hertz. Okay, so that will be our answer then here. Now the next question says, what region of the electromagnetic spectrum is it found? So we are talking about this wave. What region of the electromagnetic spectrum is it found? Now just looking at the wavelength, we need to come to understand that whenever you see a wavelength of between 400 nanometers to 700 nanometers, that is in the visible light spectra. So this is visible light. That is the region of the electromagnetic spectrum, because 625 nanometers is a part of here. All right, now the next question asks us to find the energy. What is the energy of the wave? All right, so we know that energy is given by Planck's constant times frequency, or which we can say Planck's constant times the speed of light over wavelength, it will all give us the same answer, because we know the speed of light, we know the wavelength, and at the same time we've already calculated the frequency, so we can use any of those. So what we are saying is Planck's constant is 6.626 by 10 to the power negative 34 multiplied by the frequency we found 4.8 times 10 to the power 14. So the answer we should be able to get is 3.18 times 10 to the power negative 19 joules. So that would be the energy of this wave. Alright, let's see the next question. Calculate the uncertainty in position of an electron moving at a velocity of 2.3 times 10 to the power 12 meters per second. The mass of an electron has been given. Now, whenever we are calculating the uncertainty, we need to understand they are trying to talk about the uncertainty principle, Heisenberg's uncertainty principle. So, change in position times change in momentum should be greater than or equal to Planck's constant over 4 pi. So, that is the inequality we are using. Now we want to first find the change in momentum. Okay, so we assume this electron was coming from rest, then the change in momentum is going to be mass times the change in velocity, because momentum is simply mass times velocity. So change in momentum would be mass times change in velocity if it was coming from rest. So the mass of an electron is 9.11 times 10 to the power negative 31 kg multiplied by the change in velocity, that is 2.3 times 10 to the power 12. So let's see what that gives us. 9.11 multiplied by 10 to the power negative 31 and then multiplied by 2.3 by 10 to the power 12. So what I'm finding is 2.0953 by 10 to the power negative 18. Though this is change in momentum. Now this is mass, that is in kgs, and then the velocity is in meters per second, so meter per second, so that will be the unit for momentum, kg meter per second. So I want to find the uncertainty in position. So we are saying delta x multiplied by delta p, which you have found as 2.0953 by 10 to the power negative 18, should be greater than or equal to the Planck's constant, that is 6.626 by 10 to the power negative 34. Okay, and then we are dividing that by 4 pi. So to remain with change in position, simply get change in position, we divide by this number both sides, will be greater than or equal to 6.626 by 10 to the power negative 34 over 4 pi by 2.0953 times 10 to the power negative 18. So now let's determine the change in position. So what we'll get is, we start first with the denominator, we multiply our 2.0953 times 10 to the power negative 18 by 4 pi. And that number that we find, we get the Planck's constant 6.626 by 10 to the power negative 34 divided by that answer. So our change in position is greater than or equal to 2.516 by 10 to the power negative 17 meters. So that would be our answer. Now looking at this one, this number has got 3 significant figures. This has got 2 significant figures. So just write this one in 2 significant figures as 2.5 times 10 to the power negative 17 meters. Alright, so that would be the answer for that question. Alright, let's go over the next question. Write the electron configuration and orbital diagram of an atom with atomic number of 27. So the first thing is, let's write the electron configuration. So when we are writing the electron configuration, we first need to understand some principles that we use. According to Hofbauer's principle and Handy's rule, so for Hofbauer's principle, in the ground state of an atom, electrons fill first atomic orbitals of the lowest available energy before going to the higher ones. So we're going to first fill atomic orbitals of the lowest available energy before we can even fill anything more. So this should always be in our minds whenever we are writing electron configurations. If we don't know this, we have got a video, we can go over it and view what it is talking about. So the lowest available energy is the 1s sub-level, followed by the 2s, and then 2p. From the 2p you go to the 2s, and then 3p. From the 3p you go to the 4s, and then 3d, and then 4p, just like that. Now writing the electron configuration for something that has got a atomic number of 27, the first one to be filled, again the first thing we need to understand is the s sub-level always fills up with 2 electrons. So this one always gets filled up with 6 electrons. This one, the D, will always get filled up with 10 electrons. So what we are going to have is the electron configuration. We are going to get first the 1s, fill it with 2 electrons. We go to the 2s, that will also be filled with 2 electrons. And then we go to the 2p, that will be filled up with 6 electrons. So we've used up 10 electrons so far from the 27, remaining 17. And then we go to the 3s, as we can see. It will be filled with 2 electrons. From the 3s, we go to the 3p with 6 electrons. So we filled up 6, 2 plus 2, that's 4, plus 6, that's 10, plus 2, 12, plus 6, 18. Okay. So from the 27, we have removed our 18. We are remaining with 9 electrons. So from the 3p, we are supposed to go to the 4s. We fill it up with 2 electrons. So from our 9, we have removed 2. We are remaining with 7 electrons. From the 4s now, we go to the 3d. A 3d can accommodate up to 10 electrons, but we only have 7 electrons remaining, so we have no choice but to end only there. So that will be the electron configuration of an atom with atomic number of 27. Now, what will be the orbital diagram? So when you are writing the orbital diagram, okay, the first thing is we need to write the 1s orbital, which has the lowest available energy. That is the 1s there. The next one is supposed to be the 2s on there. From the 2s, we are going to go to the 2p. Now the 2p sub-level has got 3 orbitals, so we put the 3 of them there. From the 3p, from the 2p, the next thing is the 3s, which has got only 1 orbital. From the 3s, we are supposed to go to the 3p, which has got 3 orbitals also. Now the third energy level has got 3 angular momentum quantum numbers, that is the 1, the 0, and the 2. So the 0, that is what we call the s. This is the one we've drawn here. The 1, when L is equal to 1, when the angular momentum quantum number is 1, we have got 3 orbitals, which we can see here. Now for 2, when the angular momentum quantum number is 2, we have got 5 orbitals. So we need to also write the 3d, which has got 5 orbitals. So we draw our 5 orbitals like that. 2, 3, 4, 5. So just like we can see, we can just follow the electron configuration, filling up our orbital diagram. Now we can see that we are remaining with the 4s, which is supposed to be on top of the 3d. Okay. So on top of the 3d, we have got the 4s orbital, like that. So now we start filling these with electrons. We'll be counting according to Hofbauer's principle. Electrons are supposed to be filled up first in the lowest available energy orbital, the 1s and the 2s. If we go to the 2p, we follow the Handy's rule, which says whenever you are filling up atomic orbitals, fill them first singly. If they are degenerate, if they've got the same energy like this, fill them singly before you can fill them doubly. Alright, and those which are filled up singly should have the same spin. That is the Handy's rule. So we are going to fill it like that. One electron on top, pointing on top. Another one like that. Another one. So we've used up 1, 2, 3, 4, 5, 6, 7. So we can now start coming here. 8, 9, 10. Again we come here. 11, 12, 13, 14, 15, 16, 17, 18. Now instead of us filling the 3D, the 3D has higher energy than this one. So we first fill up the 4S, which has got lower energy than the 3D. That is according to Aufbau's principle. So what we have used up is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So 19, 20, 21, 22, 23, 24, 25, 26, 27, 20. Okay, I've gone to 28. They're supposed to be only 27. So we are going to end here. So that would be the orbital diagram for an atom with atomic number of 27. So the next question and the last question which we have in this section. When light strikes the surface of a metal, electrons are emitted in what is known as the photoelectric effect. Now the question is, state the condition needed for this to happen. So the condition is the light which you are projecting on your metal surface should have frequency higher than what we call the threshold frequency. So the energy or the light which you are projecting on your metal, so that is our photon, which is simply light, or any region of the electromagnetic spectrum, anything, any source of energy which you are projecting on the surface of a metal. For electrons to be emitted from the surface of this metal, the energy with which this photon is coming should have a value, a frequency value which is greater than or equal to the threshold frequency. So we need the threshold frequency as a minimum value. So the frequency should be greater than or equal to the threshold frequency for electrons to be emitted. So that is the condition which is required. Now for B, calculate the energy needed to remove an electron from the metal if the threshold frequency is 3.4 times 10 Hz. Now we know that energy is given by Planck's constant times frequency. Planck's constant, that is 6.626 by 10 to the power negative 34 multiplied by the frequency we've been given as 3.4 by 10 to the power 10. So 6.626 by 10 to the power negative 34 multiplied by 3.4 by 10 to the power 10. We should be able to get a value of 2.25 times 10 to the power negative 23 joules. So that is the energy that is going to be needed for an electron to come out of a metal. So this is the minimum energy that should come in the metal for electron to be emitted. Anything less than that, electrons will not be able to come out. Anything more than this, the extra will be used for kinetic energy. So that takes us now to this last question. If a photon of wavelength 23 nanometers strikes the metal, what will be the kinetic energy of the electrons as they move out of the surface? So we've been given the wavelength. So the first thing is we need to calculate the energy, the frequency at which this photon is coming. Now we know that speed of light is given by wavelength times frequency. Therefore frequency is speed of light over wavelength. So that is giving us a speed of light of 3 times 10 to the power 8 divided by the wavelength 23 nanometers, that is 23 times 10 to the power negative 9. So what value are we going to find there? So that is 3 divided by 23 times 17 times 10 to the power 17. Okay, what I've just done is I've just divided these two. And then I've said this is the same base, 10 to the power 8, 10 to the power negative 9. So just get 3 over 23. And then multiply by same bases dividing, simply subtract the powers. That will be 8 minus negative 9. This is 17. So just multiply this by 10 to the power 17. So we should be able to get frequency value of 1.3 times 10 to the power 16 hertz. So this is the frequency of the light that is coming in. Now we know that kinetic energy is given by half mv squared. At the same time, when you are talking about kinetic energy, kinetic energy will be equal to the energy of the photon that has come in minus the energy of the photon required to remove electrons from the surface of the metal. So this is the energy required to remove an electron from the surface of a metal. This is the energy present. So their difference will give you the value of the speed of that electron which is coming out. Okay. So we can therefore merge these two equations. So we will say half mv squared is going to be equal to hv minus vo. So this is kinetic energy. It's the same as saying hv minus h. I'm saying this because it looks like, but this is nu representing frequency. So half mv squared, this is half, because we're talking about an electron, the mass of an electron is 9.11 by 10 to the power negative 31 kg, and then times velocity squared should be equal to the Planck's constant, that is 6.626 by 10 to the power negative 34, and then the frequency at which this photon is moving is 1.3 by 10 to the power 16. Subtract the threshold frequency, that is 3.4 by 10 to the power 10. So let's determine now, we want to find the velocity. So the first thing is, let's divide our 9.11 by 2. So that should give us here 4.555 by 10 to the power negative 31 v squared, and they should be equal to, we can subtract over that side, 1.3 by 10 to the power 16. We remove 3.4 by 10 to the power 10, and then we multiply with 1.3 by 10, sorry, we multiply by the Planck's constant, that is 6.626 by 10 to the power negative 34. So what we should be able to get is 8.61 by 10 to the power negative 18. And then we want to divide by this 4.55 on both sides. So what we are going to get is, we divide by 4.55 over this side and over that side. So divided by 4.555 multiplied by 10 to the power negative 31. So what I'm getting, sorry, let me just redo that again. So that is, we are dividing this value by our 4.555 by 10 to the power negative 31. So these are same bases. We'll simply subtract the powers. What we are going to do is, we'll just divide 8.61 by 4.5. So 8.61 divided by our 4.555, that should be able to give us 1.89. Now we multiply, so we are going to subtract 10 to the power negative 18 minus, okay, 10 to the power negative 18, we are just subtracting the powers minus negative 31, because these are same bases which are dividing, so just subtract the powers. So that is the same as saying 31 minus 18. So we are simply multiplying this number by 10 to the power 31 minus 18. So our v squared is going to give us, so we are multiplying by 10 to the power 31 minus 18. So what we should be able to get is 1.89 by 10 to the power positive 13. Now we take the square root to find the velocity. So taking the square root both sides, there and there, we should be able to get a velocity of about 4.347 by 10, okay, times 10. So this is 1 2 3 4 5 6 to the power 6 meters per second. So this is the value of the velocity that we should be able to get. As you've seen, the velocity will be so high, so the electron will be moving so fast away from the metal. And it's not actually one electron, there will be many electrons which will be moving away. Thank you so much for watching this video. Hope it was helpful.